Hello and welcome to another Solana tutorial. Today we're gonna talk about compute budget again and compute budget optimization. This is gonna be the first video of a series of videos on the compute budget and CU optimization because it's a relevant topic currently. Because there is more demand for block space and block space really is limited by compute. So that's why if we have transactions with lower compute, we can fit more transactions into a block on Solana. And that's ultimately what we want because more TPS, like real TPS. In today's video, we're gonna have a look at how you can request the correct amount of compute units, which will not only help you pay less fees, but also pack more transactions and ultimately increase the likelihood of your transaction being put into a block, which is what you want. You want your transactions to actually land, so by requesting the right amount of compute, you increase your chances to do so. So that's what we're gonna have a look at today. Then in the future video, we'll also talk about how to optimize your programs, but this video is mainly for application developers, you know, the apps that send their transactions, what they can do to increase the likelihood of the transactions actually landing and you not overpaying fees. Yeah, let's go. I found this article, I was linked this article, which essentially outlines what we're gonna talk about today. Don't worry, I'm not gonna just read the article. I know that you can do that yourself, and I'm gonna put this link in the description below. I just pasted it there, you're welcome. But I'm gonna take this one as a guideline and as an inspiration of what we're gonna do today. Because this has been a topic that's been on my mind for a while as well. And I started actually doing this in one particular use case that I will tell you about a bit later. But first we wanna understand what are compute units and maybe a bit of priority fees, because that stuff is related and I have a previous video about those topics, so you can watch that as preparation for this one. But also, we can go through it together real quick and see how to request optimal compute budget in this developer guide, how to request optimal compute budget. So yeah, all transactions on Solana use compute units, CU. If you ever see CU, that's compute units. Again, I made a video on that. Just go check that out, which measure the computational resources your transaction uses on the network. Now, how are they measured? Well, every instruction basically has some value, an operation, maybe I should say operation. And this stuff is super complicated to get it right, because you can't get it right, because depending on the architecture that the code is run, it actually needs different time to execute or different resources as well, right? One thing might be more memory intensive and one thing might be more compute, like processor intensive. And how do you weigh this, right? Because different systems have either more memory or more, right? Because not all Solana validators run on the exact same hardware. So it is really hard to get like objective measures on those things. So really the compute units are just a best guess, just so we can put a value on something. That's the one thing. The second thing I need to say about this is there is a difference between the compute units that a transaction actually uses versus the compute units that the transaction requests, because those can be very different. And that's what this entire video is about. Because if you request too few, then the transaction will just not execute because it will run out of compute. Seen that in a previous video. But for scheduling the transactions, the requested compute units are taken into account and not the actual ones, because for the actual ones, we need to already have executed the transaction to know what the actual value is. So we have an estimate that we request, and by estimate, it's an upper bound, really. So based on the requested compute units, the scheduler schedules the transactions and the requested compute units fill the blocks, I think. So if we constantly request too much, even though we need less, we're unnecessarily filling blocks, even though we could have, actually had more capacity for more transactions. That's already the entire motivation for this video. So when you pay priority fees on your transactions, you must specify the exact amount of compute units you expect to use. And not just for priority fees. This is also true for when we don't use priority fees. Side note, currently you probably want to use priority fees, because if you don't, then the likelihood of your transaction actually landing is relatively low, because as I said, currently there's more demand. Welcome to the bull market. Bull market. Bull market? Bull market. I don't know how to pronounce it because I'm not sure if we're officially in bull market, but there's certainly more demand right now. That's all I can say. Anyway, you specify the exact amount of compute units you expect to use. Otherwise, you overpay. And it's not just the overpaying that is the main issue here. It's also if you request less compute, the chances of our transaction landing is higher kind of a thing. And also, yes, if you request more than you actually use, then you're just wasting fees. But that's on you. And unless you're using extremely high priority fees, it's still not that expensive on Solana. So most people don't really care about that. So I'm going to come with the motivation that, well, if you do that right, the likelihood of your transaction landing is higher. I guess that way I can sell it better. Anyway, this guide will provide a step-by-step instruction. Step-by-step instructions on optimizing the compute units for your transaction requests. Wonderful. And maybe we don't even want to go through that guide and just look at it ourselves, because, I mean, we know how this works. We looked at this. It's just a compute budget program instruction where we set compute unit limit. That's one of the two instructions of the compute budget program. The other one being the price for the lamperts, which says how much are we willing to pay for priority. But really, this one is what we're talking about today. How many compute units do we actually request? And now the question is, if we don't want to overpay, so if we don't want to request too much, how do we know how much compute our transaction needs? Well, good thing that RPCs can simulate our transactions and spit out that value. So all we gotta do is simulate that transaction. Really, it's not that simple, but we'll get there. Let's assume it is that simple. Yeah, I'm literally gonna take that code, yo. So, we need that import. And because that's a bit small, I like it big. So you can see on your mobile phones, and my eyes see as well because I'm just blind. So what do we see here? They add a compute budget instruction with the maximum. I think that's the maximum, right? We saw that 1.4 million compute units is the maximum that you can request. So for our demo transaction, we can just say we request the maximum and then see how many we actually need. We build a version transaction and we do a simulate transaction with our version transaction. We don't check signatures, but we do replace the block hash. And if that's successful, then we return the units consumed. Just for us, I'm going to show you again the entire simulation result, and then you'll see that in simulation value units consumed, that's where the magic happens. So actually, let's pretty print that and simulate a transaction with the following instruction: a system program transfer, which will of course not work, and the simulation will tell us that, but we should still get units. Get simulation units. Okay, we need a key. Frog key. Why not? Okay, hopefully we have everything now. The connection, that's just this one instruction for now. Pair is my from key pair, and lookup tables I don't use. So let's see if that gets me anything. Pending promise. Amazing. And we can't await this, can we? Fine. I'm not really getting there, do I? Do I get an error? Oh, yes. Because if the simulation doesn't go through, then we get the error, of course. So I should actually do this up here so I see something. There we go. So that's what the simulation result will look like. We always get the context of which slot we're in when we did the simulation. And then the value, which doesn't give us logs or compute units consumed, because it will give us an error for account not found. And because we get an error, we say, oh, we don't even want it, which is weird. It should also return the compute units on error if it's an instruction error. Is that a transaction error? Yes, that is a transaction error, because account not found, we can't even get to the point of transaction execution because we can't even fee pay. Because our key pair that we loaded here and put as the fee payer doesn't have any sol. So actually, let's work on DevNet because that's easier to get sol. And then airdrop. Now that we have some sol, there we go. Now we get a different result. We're in a slightly different slot now. We're on DevNet now, so we're in a very different slot actually. This time we get an instruction error. See, not a transaction error anymore. This time it's an instruction. Well, an instruction error is also a transaction error. Watch the video on errors. Which instruction? The second instruction, because this function sneaked in another instruction as the first one, so it's the second one. And which error? A custom error 1. Which program was it? The system program, so it's 0x1 of the system program, and we know that is insufficient Lamperts. Insufficient Lamperts? Oh yeah, I mean that makes sense because I have exactly 1 sol and I'm trying to send exactly 1 sol, so this ain't gonna work. But if I were to send just half a sol or even just 0.9, then we should get a different result. Then we should actually get success. Yeah, there we go. Then we don't have an error. We get the logs. And we get the compute units consumed. We did also get the compute units before when it was failing. Here when it says insufficient Lamperts, we did get the compute units as well because the transaction was simulated. Also failing transactions require compute. The same thing. So if I want to send a failing transaction, I mean, it would be kind of stupid, but maybe you do for some reason, whatever. You can also calculate how much the failing transaction would require. And in this case, it requires the exact same. 300 compute units. That's the amount of compute we need for a simple system program transfer. Not that many, considering that we can request 1,400,000. So yeah, could theoretically do a bunch of system program transfer requests within one transaction. But if we just do one, it would be stupid if we would request more than that. Wouldn't it be, wallets? Let's see which of those wallets are smart. Let's send 0.1 sol to ourselves. Send it. So we request 200,000 compute units with this wallet. Cool. Software, we request 200,000 compute. This is the default. The default is 200k compute units. But see, how much did it actually take? And it doesn't say that anywhere really. But if we were to simulate that, then we would figure out that yes, it just took 300. So also the wallets make you overpay because they do set a price for compute and they know what's happening. It's just a sol transfer. So they could know that you could request way less. Here's a tip for you wallets. Change that. But hey, I'm not blaming them. Their focus is on user experience, not user cost savings. But hey, in terms of user experience, if you increase the chance of your transaction landing, that is better user experience. So consider that maybe. Especially for transactions where you know what's happening. Like for default transactions, I mean, it's fine that you go with like that if you don't know what they actually do. But anyway, we're getting ahead of ourselves again. So let's do a new file. Yeah, I mean, let's copy this and try and understand it because it's not that difficult. So basically what's happening here, we call the get simulation units, that's the function from before, to get our units, and then we insert an instruction. So unshift basically inserts at the first element. Inserts new elements at the start of an array. There you go. Essentially all elements are inserted at the start. That's what this unshift does. I don't know what it stands for. Who thought unshift was a good name? Opposite of shift. Right, okay, so shift removes and unshift inserts. I mean, kinda makes sense, but also weird name. Anyway, so we insert at the beginning in the instructions the compute budget instructions, once for the units, and that is a whole different story. And there's another guide on that to get the optimal priority fees, which we will not cover in this video. Here we just say 100 microlamperts per compute unit, or really it should be 100 lamperts per gigacompute unit. There are no microlamperts. Milli, micro, kilo, mega. So it should be mega compute unit. 100 lamperts per mega compute unit. But also we don't say what it's priced per, we just say it's priced in that. So because we can just specify that, we specify it as microlamperts. There are no microlamperts. 1 lampert is the smallest that you can pay, whatever. That's a whole different discussion. In this case, we'll just take a relatively low number, 100 microlamperts, what did we see Phantom use? They used 100,000 microlamperts. Yeah. And then we insert those two instructions and the rest of our instructions. Build a version transaction, compile it with lookup tables, insert the block hash that builds me that transaction. So that's what that does. If we just simulate that transaction, I can also do the same as I did with the wallets. I transfer from myself to myself. I get the result, 300 compute units were used. Now let's do the same and actually send the transaction. And before we do that, I'm gonna build that transaction without the compute budget instructions, and we will just send it. And the thing is, on DevNet, that just works because the load on DevNet is not so high, so we land transactions even without priority fees. But here we see that. Compute units consumed. Only 150 compute units are consumed by this instruction. Cool. But how many did we request? Well, the default, 200K. That one actually had 450. So the instructions to the compute budget program also seem to cost us something, which makes sense. Let's actually see how much that costs. I'm gonna add those two instructions real quick. Request 0 and the default. Wait, no, at first I just set the price. That should then give us 300 compute units, because each instruction apparently is 150, so a total of 300. And then if we add that instruction as well with the units, then we get to 450. So we see per instruction we get 150 compute units consumed, which is funny because you would think that the system program transfer actually does more, because that literally does nothing. It's not even really executed. It's just because it's in the transaction, the runtime calculates something up front, but it's not really like, it doesn't really do much. I don't know if it makes sense to call the compute budget program via CPI. I think that's absolutely useless, but don't quote me on that because I haven't actually tried. I don't know. But I would expect that doing those in CPI is just useless. But anyway, it has a price, and the price is 150 compute units. So I'm just astonished that the system program transfer takes so few compute units. But let's see, if I were to do 2 transfers, I do the same one again, haha. Is it then 600? There we go, 600, because apparently a system program transfer instruction always takes exactly 150 compute units, no matter if it fails or succeeds. So this seems pretty static, right? So always exactly 150. But let's try something different. Or actually, we first make the point of why it's a bad idea to overpay. Because for now, I mean, we pay 0 lamperts per compute unit. So really, we're not overpaying in that sense. But even so, the prioritization actually also takes into account the compute units requested, because the actual priority is calculated by the fee divided by the compute units requested, or the other way around. I'm not sure. Priority fees take into consideration also the base fee. I'm pretty sure I saw that. And what the validators actually do with priority is like also not so reliable. I mean, it's well defined, but it's not reliable because it depends on the time when a transaction hits the validator, and then it could be put into the block before another transaction which has higher priority but arrives later and stuff like that. So really this stuff is complicated. That's why I didn't do a deep dive on priority fees yet. But let's say we were to use a priority fee of, say, that 100 microlamperts. Or actually, like Phantom does, 100K. If we send that transaction, then we pay, guess what? Wait, I want to calculate that in my head because I want to seem smart and know it before I see it. So it's the base fee of 5,000. Then I pay 100K per compute, and I requested 200K. So that's 20K, right? I would pay 20K, so 25K is what I would pay for that transaction. Is that correct? Yes, 0.0025, because the 20K I paid for priority fee and the 5 base fee. But then why did I pay so much when really I get the same priority by paying way less by just requesting fewer compute? If I know that I use exactly 600 compute units, then I can say I want to request exactly 600 compute units, and then this will work the same, except that I now don't pay 20k, but just 600 times 0.1, which is 60 lamperts in priority fee. For, guess what? The same priority. Not really the same priority, because base fee is also taken into consideration with priority. So in my head, hold on, that would actually be higher priority, because the base fee is also taken into consideration for the little amount requested, which means this is actually even higher priority than the previous one, because the base fee per compute requested is higher. But anyway, not so important. Point is, we pay less and we get more. Or at least the same, because we can run this transaction. It consumes 600 compute and we just need 600 compute. And just to see that again, if I were to request not enough, let's say I just requested 500, I will still need to pay for transaction fee. Oh, no, I won't, because the simulation says computational budget exceeded. But if I tell you to ignore that, then I will pay for that transaction anyway. And again, when I just request 500, wait, there is the request. I request 500 and it needs more than 500, then it's gonna die on me, but the transaction still goes through and I still pay for it. I still pay that, the 505. But therefore nothing else is persisted, like no state changes, except for that transaction fee that I actually paid. But the transfer, even though the first transfer went through, it didn't really, because it was in a transaction with another instruction that failed. Therefore, the entire transaction is reverted and not persisted. So no state change except for transaction fee being taken. Cool. Just so we also saw what happens if we request too little, which you really don't want to do. But here's the thing. Not every instruction is so predictable in terms of their compute unit usage as the system program transfer. Let's have a look at a few others. Instead of this transfer, maybe stay with the system program, but let's create an account. Okay, let's just simulate before we send stuff. We once again need 500, but we once again go over our budget. Let's request the 200k again, just to see how much it actually takes. 600. So also, if I do 2 create accounts, it will also take 150 each. The system program is weird in terms of compute usage. And of course, I can't do that twice, because if I do twice the same, that ain't working. If I do it once, then it takes 450 and it actually succeeds. Okay, so 150 for this one instruction. It seems like those native programs don't really take up compute at all, which kind of makes sense in a way, because you don't want them to calculate how much compute they take, because calculating how much compute they take also takes compute, which is one of those weird things, which we're gonna discuss possibly in the next video when we're actually gonna optimize our programs. But for now, we see that also this instruction takes just 150 compute units, no matter what parameters I put in there. I think I can change that and it will always be the same. Okay, fine, let's do something else. Let's work with a slightly more complex program, the token program. Let's create an associated token account. That's simple. Actually, I could just create a token account and not an associated token account. Now, let's do associated token account first. So that's my instruction, and I see how much compute that will take. And now, there we go. Those are numbers that are a bit higher at least. 19k compute units for a create associated token account, which, you know, sums up those, and then this CPI, and then this CPI, then this CPI. So a bunch of stuff is happening here actually. Obviously, if we don't go through the associated token program, we can do that cheaper. So let's say instead of this ATA, we just use a new account, but that alone won't work, because first we need to actually create the account. So we also need a create, and with that create and that initialize, if we do both of them, so first the create, then the initialize. And that's also what's happening here, by the way, right? So associated token program calls the token program with the get account date. Wow, it even calls an instruction on that. Because with a new one, it can be variable. Then it calls the system program for the create account, and then it does the initialize. And all of that logging, by the way, also takes up compute. Even that log takes compute. Yeah, that this is part of the token program forever is really bad, actually, that we kept that log in, because that token program is now immutable. So this log will forever be in there, and it always takes up compute, and we can never change it. And the token program is one of those programs that is used a lot. So reducing compute units for that program would be amazing, but we can't. So that's just legacy stuff that we have to deal with here, which is unfortunate, but it is the fact. So initialize immutable owner and then initialize account 3. Okay, so it does two things. It initializes immutable and then initializes account. And here we also say how many compute units it actually consumed. Hey, does it print that automatically for all programs except for the system program? Because I never understood that actually. Why is that 87 something? Why is that? So that's the remaining compute units, I guess. Because here the remaining compute units are that many, which is the 200k we requested, minus the 300 for those two instructions. Aha, that makes sense. If we would put them on top level, then it would say of 200. So let's do the same thing again, actually, that we did before. Just do the instruction before the compute budget program. Then it would tell us, yes, of 200,000. The total result is the same. So apparently for the compute budget and for system program instructions, it's always 150. For all other programs, it's actually computed by how much they actually consume. And by actually, I mean, you know, those reference values for all the individual instructions. But that's interesting to know that system program has like always the same very little amount in compute that it needs. Yeah, so because if we now do what we said we were doing with the create account and then initialize account with 3, there we go, we also get success, and it requires way less compute, just 3.6k, because we just have, you know, those 450 for those 3 instructions, and then we still have remaining 199 of those. We just use 3100 for this one instruction. 3157. Is that also what we saw in the other one for the initialize account 3? 3158. 57, 58. So it's just 1 unit difference, but there is 1 unit difference, which is funny. And also, we already see that those can actually differ, even if we call the same stuff. Maybe that's because we did it through CPI, but I don't think so. I think it was something else. This is not a great example for compute units differ because they can depend on the state, right? You can have different branches within one instruction, and depending on the state, it does different things. Simple example, you only create a token account if the token account doesn't exist yet. I mean, that would be a separate instruction, but on the transaction level, it does make a difference in compute units. And also within one instruction. If the instruction would do a CPI to create that account or what else, like there just needs to be one if, and then we do different things. For those simple instructions, it's relatively predictable how much compute they're gonna take. No matter what parameters I have here really, the instruction always does the same thing. But let's say you were doing something more complicated. For instance, you would do a swap on Jupiter or something, right? Jupiter is an aggregator, and depending on what path it uses and which underlying pools it uses, the transaction will have very different compute. So I'm just gonna swap 0.01 sol for some Jup. Transaction reverted. I'm doing something wrong. Anyway, you'll just have to trust me that even within one application, if I do the same thing twice, it might require different compute. So, back to here. This discusses that. It says that compute units for transactions are not always stable. My example with optionally creating a token account or going a different route or, you know, some calculations just happening when we are in a certain state, or deriving a PDA in the program on chain. And if you derive that, depending on what the canonical bump is, you might need more compute to derive it. Oh, it even says that here for the find program address. There are many reasons why compute is different, so you want to figure out like what's the upper limit, right? Yeah, you basically, as they say it here, we run some tests, we simulate different transactions, and we see what's the maximum, like what's the ceiling for compute that we use, and then we set the ceiling to this. Or we say, well, we calculate it with the simulate transactions and we say it shouldn't be more than 10% more than this, or whatever percent you might go with, just to have a margin of error. You don't want to use directly what we get here, but add 10% on top of that, or even more if it's like small transactions. So yeah, depends on your use case. You might want to play with this and increase it a bit. It is safer to have it a bit higher if you want to make sure that the transaction can definitely be executed. However, what you can of course also do is use this one, or like this plus 1% or a few percent, and then send the transaction. And if the simulation or the transaction itself comes back with compute budget exceeded, well, then you gotta resend it with more compute and request more compute units. That's of course also a strategy that you can go by. So yeah, that's that. The point of this all is, and I'm gonna get big again. Point of this whole story is you don't wanna request more compute budget than you actually need to request, because we wanna fill the blocks efficiently. And if that's a too altruistic worldview for you, then you wanna not request more than you need, because your transaction is more likely to be included in a block if it can be fit in there. And let's say the block only has so much compute budget left for more transactions, then if your transaction is small, it might still sneak in there. And small, like transaction size, in this case, is determined in compute units. So not only do you pay less for transaction fees, like priority fees, if you choose to use priority fees, you also get higher priority per default because of base fee, and you have a higher likelihood of your transaction to actually land. So request the right amount of compute units. Of course, you also definitely don't want to go below, because then your transaction will just fail because you run out of compute units. But you want to find like a good middle ground where it's safe. You're definitely above what you could possibly need, but you also don't want to request like the 200k default if you know that you need less. If you need more, then you want to request more, of course, if you have like a big transaction. But yeah, try to be as accurate as you can here. That will just increase the likelihood of transactions landing. Depending on the state of the cluster, maybe not by that much. But yeah, as they say it here, wallets, dApps, and other services should ensure their compute unit requests are optimal to prove the best experience possible for their users. Yes, exactly. Optimal. Of course, there is no optimal. It's always a trade-off between too much and too little, too many or too few or whatever, right? Unless you know exactly how much compute you take. If you just do a system program transfer, as we saw, then that's a fixed amount of compute and that will never change. So there you can use the optimal value of 150 compute units. And if you actually do the compute unit instruction, then you need another 150, so it's 300 in total. And then you might also want to do priority, so then it's 450 in total. But you get the point. We saw this today. Here we can actually be optimal, but as soon as it comes to other programs, you want to have a little bit of a buffer, or you're risky and you just simulate the transaction and you're like, it's unlikely for that to change between simulation and when I actually execute it, which in most cases, it is unlikely. You can always simulate the transaction before you send it and request the right amount of compute. Or after a while, you just know how much compute your transactions always need. So you always set that with a certain margin. You know, that's up to you. Obviously, simulating the transaction takes a bit of time because it's one RPC request. Also, it increases your RPC request. So you might not always want to do that for all the transactions of your application. But overall, getting the ballpark right would be a good first start. Again, I give you the example with the system program. If you just do a transfer, then you don't want to have the 200k compute units. And with that, I want to conclude. Watch those other videos, like this one, subscribe if you haven't already. This is not gonna be the last video on the topic of compute unit optimization. We're gonna talk more about that in future videos. So stick around and I'll see you there.